Hello, I'm Zach Evans, and with Will Sasadu for a telecommunications SLED project, we built a DIY ground station to capture real-time Earth imagery from the METEOR M2 satellites orbiting about 800 kilometers above us. Most people assume satellite communication requires extensive specialized gear, but I wanted to prove that with a solid understanding of antenna resonance and signal processing, you can downlink high-res data with less than $50 of hardware, as shown here, and some repurposed metal co-hangers.
Yeah, so the build process was straightforward but still pretty precise. We started by constructing the V-dipole antenna using two metal conductive coat hangers. Each one was cut to 52 centimeters of length. That way it would resonate at our target frequency of 137.5 megahertz. And then we mounted these at a 120-degree angle using a custom PLA 3D printed base to ensure that we had a wide directional receiving range. And then to actually get the signal to the laptop, we soldered the two antenna wires to an RG58 coax cable. And the reason we chose that is because its 50 ohm characteristic impedance matches the characteristic impedance of the actual antenna wires, so that minimizes the reflections we see and the power loss as a result. And then after a quick proof of life test that we did using local FM radio stations and actually hearing them using SDR++, we confirmed that our hardware was receiving good clean signals and we were ready for the actual satellite pass.
Receiving data from fast-moving satellites is much harder than picking up a stationary radio tower. We use SatDump to track the METEOR M2-4 orbits, waiting for a high elevation pass, ideally over 60 degrees, to clear local obstructions. After several unsuccessful attempts at urban spots like the Colk rooftop and the Tech Green, we moved to Metro Atlanta and were able to get a reading at about 1.5 feet above the ground. As the satellite crossed through the horizon, we saw the characteristic signal hump at 137.9 megahertz. We recorded the raw LRPT data for the duration of the 10-minute pass and manually adjusted antenna orientation to maintain a stable signal-to-noise ratio.
So this is the most rewarding part, turning that raw electromagnetic wave data into an actual image. So we started by feeding our recorded .wave file into SatDump's offline processor, and we used the LRPT 72K decoder. And LRPT stands for low rate picture transmission, which is the kind of transmission that the METEOR satellites use. And so even with some minor signal dropouts that we had during the pass, the software was able to successfully decode and reconstruct these views of the eastern United States. And you can clearly distinguish cloud patterns and coastal boundaries. And we also used the fill missing data and RS check features to clean up some of the noise and overlay GPS accurate land borders onto the images. And I think that just seeing a live image of the planet that you personally pulled from space, literally using coat hangers, is just such an incredible application of the theory that we've been studying here in the ECE department at Georgia Tech.
This project bridged the gap between textbook antenna theory and real-world execution. It proves that with a little bit of engineering and some accessible hardware, the entire world, and even space, is within reach. Thanks for watching.